So probably the most obvious way to, actually I should not, have you done the back of the envelope time calculation of the strength of the wave and argued that neutron stars are the most likely stars to, I don't know what you've done, sorry, I should have been attending your class.
We've done quadruple formulas and they know that the neutron stars and black holes are
the most likely okay, so I won't do that.
Are about the only things that we're going to see except where the LIGO, except for speculative things like
neutron stars.
Like the beginning of the universe.
Right. Okay, so there are various processes that people have proposed for having neutron stars emit detectable amounts of radiation. So let me try to summarize what's known about some of these today. The simplest to understand, I think, are emission processes that are associated with the fact that neutron stars, after they are a few months old, cool to the point that they develop a crust, a solid crust. So you could imagine that in this solid crust you could have something like mountains, and as the neutron star rotates, this mountain would cause a time-changing quadrupole moment, which would then emit gravitational radiation. So thinking of that kind of process, you have to think of how can neutron stars plausibly develop large enough mountains that they can emit enough radiation that we could actually see them with the kind of detectors that we're in the process of building right now. And I think there are basically three mechanisms that people have thought about that might work. I don't think any of these are really guaranteed the most likely sources we'll see, but they're possible mechanisms that one might imagine. So this first thing I want to talk about is emission of GR from solid neutron star crust type. So one of the easiest ways to get a non-symmetric shape from a crust is neutron stars typically are rotating. And so you can imagine having a rotating neutron star. As it rotates, the rotation causes a flattening or an oblateness of the star, right? The equator bulges out, the poles get a little thinner. And you can imagine having a star which is rotating fairly rapidly at the time that the crust forms, and so frozen in to the structure of this crust would be an imprint of the rotation that it had at the time that it cooled. Okay? Then you might imagine that something else happens later on in its life in which the angular momentum of the star was changed somehow. For example, you could imagine that this neutron star is in a binary system, and that the companion star at some point becomes large and starts dumping material through its Roche lobe onto the neutron star. So you can imagine that there's another star in orbit around this. The other star gets large as it goes through its nuclear evolution. Some of the material from that secondary star escapes and gets accreted onto this star. Now, if the orbital plane of the second star isn't exactly aligned with the axis in which this deformation was frozen in, you can imagine that this star would be spun up around, gaining angular momentum in this new direction having to do with the accretion. So there might be some other direction, say that one, about which the star ends up rotating because of some accretion process. Okay, and so now there is some angle, theta, between the symmetry axis of this frozen-in deformation and the new angular momentum or angular velocity axis of the star. And as a result, in the inertial frame, there would be a time-dependent quadrupole moment associated with this. So the effective ellipticity that goes into determining how much radiation is, of course, not just the frozen-in ellipticity. Let's call that E sub d, using the notation from this paper that Cutler and Thorne just wrote. You can read the timescales and things in, or the strengths of the fields and things in there. So, of course, if it were rotating around the symmetry axis of this, there would be no radiation at all. So the effective ellipticity is some product between this angle and this frozen-in field. So the effective, something like that for small angles. Okay, so that's one mechanism. We have a frozen-in field, which then gets, or frozen-in shape, which then gets its angular momentum changed by some later process. Another plausible idea is to have non-symmetric magnetic fields. So you can imagine having a neutron star which is basically rotating around this axis, but then it has built into it some very strong magnetic field, and this magnetic field has anisotropic stresses that can deform the shape of this star in some non-axisymmetric way. And so then, as the star rotates, this non-symmetric shape that's caused by the deformation in the magnetic field could also radiate, in principle. And a third possibility are thermal effects. This is an idea that was proposed by Lawrence Bilston a few years ago. So let's draw a picture of a neutron star, and I want to draw a surface of constant potential, say the constant pressure in the star. And let's imagine that there is some process that has the temperature associated with the material on this isopressure surface in this part of the star different. So let's have a plus delta T here, and for some reason there is a shortage of temperature in that region. Okay, so how can that affect the star? Well, if you're in the density layers in the star where there is an equilibrium between neutrons and protons and nuclei, then changing the temperature a little bit changes slightly the distribution of which nuclei are actually in beta equilibrium at that, on that surface. So by changing the temperature a little bit, you can change the most stable nucleus from being, I don't know, whatever it is, yttrium-237 to strontium, I don't know. So you can have different nuclei being the stable ones, and these different nuclei can have different numbers of neutrons and protons in them, and consequently the density associated with the material, even though the pressure is the same here as it is here by assumption, the density can be slightly different in this region where the temperature is slightly higher. Okay, and Cutler and Bilston have argued that if you can have temperature variations around constant pressure surfaces that are on the order of 10%, which is pretty huge actually, so if delta T over T is approximately 10%, then you can get a lot of gravitational radiation out, enough that you could actually plausibly see it. Okay, so why should anybody believe that you could have 10% temperature variations around constant pressure surface? This has always seemed fairly implausible to me, but it occurred to me as I was thinking about these notes last night that one mechanism for doing this might actually be magnetic fields. The thermal conductivity is very different in a region where you have magnetic fields. And so the conductivity along the magnetic fields is very different than the conductivity perpendicular to the field. So it's conceivable in these systems that they're talking about where you have material accreting onto these stars in low mass X-ray binaries, and that material is being burned in a nuclear process at the bottom of an ocean of the hydrogen that gets accreted on, that the heat from that could be transported away in some asymmetric way. It could get much cooler going out in the direction where the magnetic field is, for example, than in other directions. I don't know. I think all of these possibilities are fairly speculative. Yeah.
Why do you find that 10% temperature anisotropy implausible if you have accretion that's occurring locally due to the magnetic field?
Well, most of the energy is not coming from the accretion in these objects. Most of the, there's a couple of things. So it is true the accretion is happening in some local way, but the hydrodynamic timescale, so say you took a lump of accreted material and you put it up here on the surface of the star, you ask how long does it take this stuff to move around the star? Well, it's like saying if I took a bucket of water and I put it in the middle of the Atlantic, how long does the shape of the bucket stay there? Well, it's not very long. It's a hydrodynamic timescale. It just flows. So it's hard to understand how you can get long-term anisotropies from the fact that the accretion is happening at one place rather than another place. Secondly, the place that the heat source is coming from is not from the accretion itself, but the heat is actually all generated down in a layer. So the top part of this neutron star is basically hydrogen, it's stuff that's coming on, and it builds up until the density at the bottom is so high that it ignites and starts burning. And most of the heat in this process is coming from this burning layer. And of course, that's going to happen essentially everywhere around the star, as long as you're at a deep enough depth to cause the reaction to go.
The energy from accretion is 10 times higher than what you're going to get from polynuclear burning or more. I mean, it may just be radiating off the surface.
Yeah, so that
is a lot more energy.
Right, but so these guys say, and the reason must be that the energy from the accretion just gets radiated as X-rays, and that it somehow doesn't penetrate down to actually get the star hot. I don't know. Should have Lars give this lecture if you want sort of accurate and correct.
More euphoric.
Right, and more enthusiastic defense of this mechanism. Okay, so whatever these mechanisms, and there's probably many more that we haven't thought of, you can nevertheless ask the question, how big a mountain do we need in order to be able to actually see it with the detectors that are being built? And estimates for that you can read in this paper that Kip posted on the web that he and Cutler wrote, this review article. And so let me just write down from that paper what the estimates are. So if you have a source, they say, whose frequency is known, that is, you have a neutron star that you can observe in some way, and you could observe its frequency, for example, it's a pulsar or something, so you can know exactly what its frequency is. Then they claim that you can measure gravitational wave from such a source if this epsilon, this measure of the non-axisymmetry or non-sphericalness of the object, is greater than 2 times 10 to the 8th for a source whose frequency is 1 kilohertz, and it scales like 1 over f squared, which is located at 10 kiloparsecs away, and it scales like that. Okay, so this is for known frequencies. Typically, these systems are complicated. They come in these objects called low mass X-ray binaries, so it's a neutron star, there's a companion star which is dumping material onto the neutron star by accretion, and that accreted material changes the angular momentum of the star, right? It continually spins it up, and it does so in a fairly unpredictable way because the accretion rate isn't exactly constant. So this frequency tends to evolve with time in a way which isn't particularly predictable, and it may not be observable directly. So you may not know exactly what the frequency is. And in that case, Cutler and Thorne estimate that you need to have stronger gravitational waves because you don't know exactly what frequency to look for. They say you need epsilons bigger than 10 to the minus 5 for objects radiating at a kilohertz located at 10 kiloparsecs. Okay, so how big an epsilons can you actually expect? Cutler and Lars Bilston and Greg Ushimirski have done a number of calculations. This is written out of your paper, Kip. Sorry, here.
Contrast between those two numbers doesn't look right.
Well, complain to the authors. That's all I.
Yeah, factor 20 contrast. Anyway, I'll go back there.
Yeah, so it's bigger than that, according to to the paper. So you ought to fix it if it's wrong. So the question is, how big an epsilons can you actually expect? And Kurt Cutler and these guys have produced plausible upper limits. Of course, it's plausible. You have zero, right? Things can be completely symmetric. You can never rule that out completely. But they've argued that you can expect to have some plausible So they argue that you can expect to have epsilons which are up to about 10 to the minus 6. So if that's true, and if Kip's number in the paper is right, then it seems unlikely that you'll be able to observe these unless you can determine the frequency of the object in some other way, but that it might be plausible to detect them if the frequency is known, at least if that number is right. If it's an order of magnitude smaller, as Kip thinks, we might be in trouble there too. Okay, that's all I know about gravitational radiation from solid objects. That's the most sort of obvious source of gravitational radiation, but neutron stars can do other things. Neutron stars do have crusts, but the crusts are fairly thin and weak, and it's reasonable to think of neutron stars as basically being fluids. So you can also have gravitational radiation from the pulsations, the oscillations of the star. So from neutron star pulsations. So you can imagine having a star, looks like this, say, that gets deformed in some normal mode, which oscillates back and forth. If this normal mode is one which has a time-varying quadrupole moment, then it will emit gravitational radiation, and in principle, we could detect it. So in most cases, if you take a neutron star and you excite an oscillation, it will emit gravitational radiation, but the gravitational radiation will just tend to damp the mode out, right? It'll take energy out of the mode and radiate it away to infinity. So the amplitude of the mode just goes down exponentially as you radiate the radiation away. Also, these modes tend to shear the fluid, and whenever you take a real material and cause it to shear, there are viscous forces which convert the mechanical energy of the oscillation into heat. So these kinds of modes of stars tend to get damped away in reasonably short timescales. So in astrophysics, it's true that if you had an oscillating neutron star which was sitting right next door, and if it somehow started oscillating, you could detect the gravitational radiation from it. But the trick is how you get it started oscillating in a plausible astrophysical way. So the only mechanism that, well, people have talked about all kinds of what I think are implausible mechanisms. For example, if you had a neutron star which had some kind of gravitational encounter, a comet comes in and goes orbiting past it, well, the gravitational interaction, the tidal interaction between the neutron star and the comet would cause it to start oscillating. But how plausible is that really, right? I mean, it could happen, but it's not the kind of thing that you would expect to happen very often. So in order to get something that we think that you could see in real neutron stars, the only mechanism that people have thought of is if you have a mode which is unstable for some reason. Okay, so if you have an ordinary mode, it tends to get damped away. The dissipative forces of viscosity inside the fluid or the active emitting gravitational radiation itself just takes energy out of the mode and just dies away. So unless there is some way to drive the mode, some process that makes it maintain its amplitude, or if the mode was just unstable, so it wants to grow exponentially for some reason, then only in a situation like that might you expect to be able to get enough radiation to make a difference. So unstable So that also sounds fairly implausible. Right? It was unstable. Why wouldn't it just blow up? Why would we expect any real neutron stars to have instabilities? But it turns out there are a class of instabilities which people think may actually happen in neutron stars and which, in fact, could cause gravitational radiation. So what must these modes look like? So if you had a non-rotating neutron star, you can think of different kinds of modes. You can think of the simple modes which are just radial breathing modes. Okay, so the star stays spherically symmetric and its radius just gets bigger and smaller. So stars certainly have modes like this, but they don't emit gravitational radiation. So we don't care about them, at least in this context. And in fact, some of these radial modes are in fact unstable. For example, the mode that causes a white dwarf to collapse into a neutron star when the mass is too high is exactly one of these radial modes. If the mass is beyond the stable point, then there is one of these modes that instead of just oscillating, it just exponentially causes the radius to decrease and become a high-density neutron star. So there are unstable radial modes, but we don't care about them. They don't emit radiation. There's a theorem that says if you have a non-rotating star which is stable to radial oscillations, then in fact it's also stable to all non-radial oscillations. Okay, so you can certainly have non-radial modes in a non-rotating star, and those modes would radiate gravitational radiation, but in fact if the radial modes are stable, then the non-radial ones are as well. So they're not particularly interesting. We don't have any way of driving them to make the amplitudes large enough to emit enough radiation to make a difference. So you have to give, so non-rotating stars are boring, is the bottom line here. You've got to go look at rotating stars. And in rotating stars, people have studied pulsations and instabilities for literally hundreds of years. And I want to tell you a little bit about the history of this, partially because it's relevant and partially because the language people now use to describe various kinds of instabilities is all based in this old historical literature. So if you want to understand how people talk about things now, you need to understand the language that was developed for these old guys. So there are two classes of instabilities of rotating stars. So we're going to talk about instabilities So the first class are called dynamical instabilities. And these instabilities have the feature that the force, if you like, that is driving the instability is the same force that is responsible for the restoring force in the pulsation itself. So you can think of a star as a spring, and these modes are just normal oscillations of a spring. The spring force are typically things like pressure. You can press the star and the pressure pushes back, and the star just oscillates. So when the restoring force for the oscillation is the same force that is driving the instability, that kind of an instability is called a dynamical instability. And so typically those instabilities are hydrodynamic in origin. Neutron stars are basically fluids, and the forces are typically hydrodynamic things like pressures. The timescales for these instabilities, because they're being set by hydrodynamic forces, are typically comparable to the pulsation period of the mode. So the timescale So for a neutron star, a typical pulsation period is a millisecond or a fraction of a millisecond. And so the time scale for the growth of the instability is comparable to that. And so therefore, the amplitude gets large very, very fast, typically in these these are very strong instabilities that tend to make things happen quickly. There's another class of instabilities. I've lost my eraser. It's another class of instabilities called secular instabilities. Secular instabilities have the property that the force that's driving the amplitude of the mode to become larger is caused by dissipation of some sort. So for example, viscosity might be the driving force, or gravitational radiation itself might be the driving force that causes the amplitude of the mode to grow. So in secular instabilities, the instability So if there were no dissipation present, then in fact these instabilities go away. That is, the time scales become infinitely long. So the time scale is proportional to the time scale is inversely proportional to the strength of the dissipation mechanism. All right. So those are the two basic types.
So that bottom number should be a few 10 to the minus 7 on the right, where you were getting ready to erase that.
Are you telling me this or asking me this?
The bottom number, the top is right.
Oh.
The number is a few to 15 times the bigger.
Okay, so it's about 10 to the minus 7. Okay. Thank you. So that means this is possible too. Good.
That's for an all-style frequency search.
Yeah. There are some other typos in that paper that we should discuss privately later, but this. So the first class of stars that people studied instabilities in are these very simple Newtonian stars that people call Maclaurin spheroids. So these are uniform density. Newtonian. Okay, so these stars turn out to have exactly elliptical shapes. So they're completely uniform density. The shape of the star is determined by the angular momentum. If the angular momentum is 0, then the star is just spherical. As the angular momentum increases, the oblateness of this spheroid gets larger and larger until it turns into a sort of very thin pancake. Actually, and the limit is the angular momentum goes to infinity, it becomes infinitely thin, infinitely large pancake. So people studied the instabilities in these objects. In fact, the dynamical instabilities in, these are called Maclaurin Spheroids. So that's the historical name. Maclaurin is some Scottish mathematician from 60 something, who first wrote down the solutions of the self-gravitating hydrodynamic equations for them. The stability of these was actually first determined by Riemann, the same Riemann as in Riemann tensor. And he looked at the modes of these. So now I'm thinking of looking at the surface of one of these things from the rotation axis. So I'm looking down on the star. It's rotating around, say, counterclockwise here. And he looked at the class of modes which turn this into an ellipsoidal shape. So it just deforms it a little bit. It's uniform densities, so this is supposed to be deformed in a way so that the volume of this squished ellipsoid is the same as this, as the one you started with. And then this pattern can rotate. There's actually two modes of this sort. One propagates around in the same direction the star rotates, and the other one propagates the other way. Okay, so these are quadrupole modes. They have sort of spherical harmonic numbers L equals M equals 2. And let me show you a graph. Well, I don't know whether I want to write the formula first or show you the graph. So he computed the frequency of these modes, and the frequency has the following formula. The two modes have frequency omega, where omega is the angular velocity of the star. So this is the angular velocity. And then there's some complicated function, which in Chandrasekhar's notation is called B11 of omega. And so it's some complicated function of the angular velocity. It has the properties, I could write it down, but you can look it up if you're interested. It has the property that as omega goes to 0, this just goes to some constant. So in that case, the frequency of these two modes just go to plus and minus some number. Okay, as the angular velocity increases, okay, so this is some fixed constant at omega equals 0. As omega gets bigger and bigger, you have two real frequencies, which are the plus and minus of the square roots, until omega equals 4b11. So for omega squared is greater than 4b11 of omega, then this frequency has a complex, has an imaginary part. Okay, and so one of those imaginary part, so if the imaginary part is positive, then the frequency grows exponentially with time. If it's negative, it dies out exponentially with time. And so one of these modes is unstable. It's unstable on a time scale, which is just determined by this hydrodynamic stuff. So I'll show you a graph of this in a minute. But the size of the imaginary part of this frequency is comparable to the frequency of the star itself. So this is one of these dynamical instabilities. It happens in this case. So let me show you this graph out of Chandra's book called Ellipsoidal Figures of Equilibrium. So this shows a graph of, Chandra never plots things the way you think you would if you were writing the book. So he plots a quantity called sigma, which is this frequency of the mode plus 2 omega. So that sigma is actually the frequency in the co-rotating frame of the fluid rather than in the inertial frame. And he plots the absolute value of it instead of plotting the number itself. And so what he has here, in this axis, is the eccentricity of these Maclaurin spheroids. Okay, so that's a measure of how fast the star is rotating. When the eccentricity is 0, the star is not rotating at all. When the eccentricity is 1, that means it's an infinitely flat pancake which has infinite angular momentum, and things in between correspond to stars rotating at various rates. There's an analytical formula that tells you the relationship between the eccentricity and the angular velocity, which you can copy out of his book, but it's not particularly enlightening, so I'm not going to write it down. Okay, but let's look at this graph. So for 0 angular velocity, these 2 points coincide, and that's because he's taking the absolute value. So that corresponds to this plus and minus the square root of b11 at 0 angular velocity. So this curve should really be folded down to negative frequencies. As the angular velocity of the star goes up, this negative guy gets larger and larger. At some point it crosses 0, and the frequency of the mode changes. Actually, at this point, a secular instability sets in. And then at larger angular velocity, the frequencies of these 2 modes coincide at this point. Okay, so that's the point where this guy goes through 0. Okay, and then beyond that, what happens, this curve is the real part of that frequency, and the real part, you can see, is just omega. So above this point where the star has gone dynamically unstable, the real part of the frequency of this mode is just the angular velocity of the star, and this little dashed curve down here represents the imaginary part of the frequency, which is the stuff that comes from this square root. Okay, and you can see that the size of this imaginary part is comparable to the size of this real part within a factor of 2 or something like that. Okay, so this is the classic case of dynamical instability. And what it tells us is that in order to have dynamical instability, you've got to be rotating pretty fast. Okay, this doesn't happen down here near non-rotating stars. If you're going to have this at all, you've got to have the star rotating really pretty quickly. I mean, this 1 means it has infinite angular momentum, and so you have to be pretty close to that in some sense. A quantity that in the literature is used to measure the angular velocity of these stars, so here Chandra has graphed this in terms of the eccentricity, that's not a particularly popular measure of angular velocity. Yeah?
I think angular momentum means that all the masses have angular momentum, right?
So what I mean by angular momentum is just Newtonian angular momentum. You just take the angular velocity of the star times its moment of inertia, and that's it. Okay? And so the way it becomes infinite, so you take a fixed mass of material, okay, and when you change it from one ellipsoid to another, because the mass is constant, we want to keep the volume of these ellipsoids the same. Okay, so I start with a spherical one, and now I make it more and more elliptical, keeping the volume the same. So as it becomes very flat, that means its size has to get huge. So that means its moment of inertia, that goes something like mr squared roughly, is comparable to r, the radius. But that's going to infinity as you take the limit that this thing becomes infinitely flat.
Yeah, what I was thinking was that the mass would also go to infinity as the angular momentum goes to infinity, because the rotational energy goes to infinity.
So
I'm thinking relativistically, not.
Okay, so that's right. So this is Newtonian, and I'm fixing the mass. I'm comparing objects that all have the same mass, and I'm comparing a series of objects with the same mass but different angular momentum, and I'm considering this limit as the angular momentum goes to 0. Okay. The other parameter that people use to measure the rate at which stars rotate, is called beta in some literature. It's also called T over W in some literature. So this is a measure of rotation. And T is the rotational kinetic energy of the star. So you just take the integral of the mass density, this script pi, which most hedons like me call pomega. It looks like an omega, but it has a curly top. So pomega squared times the angular velocity squared. Pomega is just the radial cylindrical coordinate. It's x squared plus y squared, if you like. So that's the rotational kinetic energy of the star. The gravitational potential energy is just the integral of the density times the gravitational potential. And you can see that in the limit that the angular velocity go to 0, the rotational kinetic energy goes to 0, the gravitational potential energy goes to some fixed value, so beta goes to 0 for non-rotating stars, and it gets bigger as the angular velocity increases, and therefore as the rotational kinetic energy increases. So people use this beta as a way of measuring angular velocity for historical reasons that I don't totally understand, but it's useful to keep in mind what the values of beta are that correspond to these instabilities in the Maclaurin spheroid. So the dynamical instability in Maclaurin occurs at beta is about 0.27. That's the point here where these two modes join and where the square root, which I have now erased, goes imaginary. That corresponds to an eccentricity, which I wrote down someplace, of about 0.95, but this 0.27 number is something you see in the literature all the time. The place where this crosses 0, which actually corresponds to a place where secular instability happens, is at 0.14. Okay, so that's the historical context in which we understand these instabilities. We know that secular instabilities typically happen at lower angular velocities than dynamical instabilities. They tend to be weaker. That is, the time scale for them tends to be much longer than the time scale for dynamical instabilities. But for a dynamical instability, you need to get the star rotating really, really fast. Okay, so if this is going to happen in astrophysics, we need to have a plausible mechanism for generating really, really rapidly rotating neutron stars. So how do you do that? There are basically three ideas that people have thought about in which you could plausibly get very rapidly rotating neutron stars. They're all basically related, but so one, how do you form neutron stars at all? The standard mechanism is you have the core of some nuclear burning main sequence star collapse when the mass of its core becomes larger than the Chandrasekhar mass. Okay, then there ceases to be enough pressure to support the core, and it just implodes. So degenerate. So here's this white or this red giant star. It is burning nuclear material, so in the middle here you have the ashes that result from the burning process, say carbon and oxygen. The mass of this burnt material builds up until this is large enough the mass of this becomes large enough that it can no longer be supported by the thermal pressure that exists in the center of the star. It starts being supported by electron degeneracy pressure, and then that can happen only until the mass of this core is something like 1.2, 1.4 solar masses, depending on exactly what the makeup of the material in the core is. So when that happens, it collapses. Well, when you have an object which may have a little bit of angular momentum collapsing, as it collapses, the angular velocity increases, okay, in order to conserve angular momentum. So say the angular momentum of this core is J. The core has some mass M and some initial moment of inertia, which is something like, no, this is what I want to write. It's the moment of inertia times the initial angular velocity, sorry. And the moment of inertia initially is something like the mass times its initial radius times its initial angular velocity. This has to roughly be conserved during the collapse process, and so you can get a relationship then between the final angular velocity of the star and the initial angular velocity in terms of the ratio of the initial and final sizes. So if this initial core is something like a white dwarf, which has a size of about 1,000 kilometers, and the final object is something like a neutron star, which has a size of about 10 kilometers, then this ratio is something like 100, and squared is something like 10 to the fourth. So the angular velocity of the final mess that you get after the collapse tends to be a large multiple of the initial angular velocity. So even a fairly slowly rotating initial configuration can end up fairly rapidly rotating via this mechanism. Okay, a related possibility is called the accretion-induced collapse of white dwarfs. So here, you have some white dwarf star, which is in orbit around a main sequence star which has started going through its red giant phase, and it swells up, fills its Roche lobe, and then starts accreting material onto the white dwarf. Okay, the accreted material, what? You have to change something?